Hello and welcome to this tutorial. My name is Frederik Steinmetz, and today I'd like to present to you the third part of this series. If you haven't watched the first two parts, I would highly recommend to do so, unless you're very familiar with the animation nodes in the first place. Before today, we used these mathematical constructs called Epitrochoid, Hypotrochoid, and so on in 2D space, meaning the entire construct had a z value of 0, which made it flat. It was still nice to look at them from the top, but still, we're in Blender, we're in 3D, so I'd like to make these structures 3D. So if I press play here, you can see the structure is three-dimensional, and I actually made this react to music. This is not part of the tutorial, but if you want me to do that, leave a comment in this comment section and I'll see what I can do. Alright, you can see from here we get this wave structure, and I did this by experimenting a lot with the z values. I'm going to show you a simple case in the tutorial, and then I'm going to give you the code, the actual code I used for this one, for the z value, because as I said, it was try and error, and describing what exactly I did would just take forever. So this is the setup. You might be familiar with this part because I didn't change anything, but last time inside this loop I used expression nodes. The expression nodes allow me to use one line of whatever, in our case it was math, to take any number of values and output something. Now I want to, for simplicity's sake, use a script for the entire thing, because if you use an expression node for every line, that will be quite cumbersome. So you might remember those are the two lines that I just copy pasted into the expressions, and we're just going to leave them inside the script for now. In the attribute nodes, you can only use one line, which means that the modules used for math and so on are already imported. And to save overhead, they are not if you use a script node. So we have to specifically tell Python what cosine and sine is, because it's not a native function of the Python library. Instead, we need the math library, and to do that we could just write import math. But I don't want to import the entire math library when all I need is cosine and sine. So from math, I want to import sine and cosine. So now Python knows exactly what cos and sine are, because they are modules of the math library, or operators rather. Now at this point we could already invoke the script. It would give us an error message if the auto execution was on, but still I'm going to do that right now because I can't insert this without causing an error message. So with the subprograms I want to invoke something that's not there yet, so I'm going to invoke a new script. And of course I'm going to choose the one we just did. Now if I were to execute the script, it would give me an error message, and the simple reason is Python has no idea what capital R, small r, and T and D are. So that wouldn't do anything, and maybe we should call this something so we can find it later. And now this script, as I said, it doesn't know what R, R, T, and D are. It doesn't need to know what X is, because X is on the left side of an equal sign. So as soon as you write an equal sign on the right side of a variable name, Python knows by whatever this is what type the X is, meaning this outputs a number, so X is a float. If I were to write X would be a string, and this does not throw an error message because Python is not type safe, which means I can use any variable and assign any valid value. It doesn't matter what it was when I used it the first time. So let's not do that. And we need, as I said, inputs for capital R, small r, T, and D. And even though it might not be good practice to use capital R and small r in your inputs, you will see in a second. As I said, we need 4 floats. So click first and then type in float Okay, now we have 4 floats and they need to have the exact name as in here. That's very important. And you can see there's no way to use duplicates. So it just adds random stuff in behind your float name. So this would be T, because T will be on the top because it will come from this node, which is on top of the loop. The second one, just in order, capital R, small r, and D. Okay, as soon as we invoke this, you will see why it's not a good idea to, so I'm just going to do that. And the labels on the invoke subprogram list actually make the small r to be a capital R. But I don't want to spell out radius every time I use it here, because, well, it just blows up my code. So we only have to remember at one point that this is the small radius and there's the big radius. And one more reason why I don't care is I'm toying around with these values anyways. It's not like I have a list of values that I found somewhere and it's very important that I use this for the small radius, this for the big radius. And of course the small radius can be bigger than the big radius. That doesn't matter in the slightest. All I want is to toy around and see the results immediately. So don't care. Good. You can see we need, of course, a vector output from this script because we have it inside a loop that is supposed to create a vector list. So we need an output, which is a vector, and we need to give this a nice name. So I'm just going to call this position. And of course, if it's called position, I'm going to hover over this and press Ctrl C, and I'm going to say position is a new vector. The new keyword does not exist in Python, so we just type in vector and then 2 parentheses open, and that is because a variable with a constructor is always declared with 1 open parentheses, and the vector takes 1 tuple, and tuples in Python are parentheses and then n values separated by comma or parentheses. So that would be x, y, and z. And that would be the closing parentheses of the tuple, and that's the closing parentheses of the vector declaration. And now we would still get one more error because Python has no idea what z is. I'm going to use z equals 0 for now, just so we don't get an error message. So in theory, if I didn't do anything stupid, this should already work. But it will not output a valid position, because as you can see here, we're dividing by small r, and small r has a value of 0. So not a good idea. Everybody who's ever done that on their calculator will confirm that that's not a good idea. And we're going to use values for these. Now, I could use these sliders in order to control the script. However, that is not considered good practice. What I want in the end, I want to never have to touch this node again and never have to touch this loop again, the entire loop, everything what's in there. I don't want to have that for the user. In most cases that would be me, but even especially if you give this to someone else, you would not want them to mess with the values inside your loop. You want to change this node and this node only. Maybe some of the smoothing, maybe different spline, but this is my main node. And this loop I do not want to touch ever again after we're done. Okay, so I'm going to use again a couple of floats. And you can see here it doesn't add the random extensions to the float value, because you can have as many names, as many different names, as many equal names in your list here as you want, because they're not assigned, they're not correlating to any names in a script. So we already have the T covered by precision. So I'm going to call this big radius. And as soon as I connect this, I never have to worry about the naming convention in here again, because this one tells me this is the big radius, and this one I know because I did it a minute ago. I know that that's the capital R, and this one, and this one, and now we don't have to worry about the naming conventions in here anymore. This one was our T, this one is our D. I don't know what it stands for, so I'm just gonna let it call it D, And this float, I made one too many because I already had the t. It doesn't matter. I'm going to assign that later. All right. And since we have the position, we can already connect that. All right. So now we still have the small radius at a value of 0. And the big radius, oh, I'm just going to use the values from Wikipedia, 6.3 and I don't know what it was, 2. Doesn't matter, we're experimenting anyways. So fingers crossed, let's pray execute node tree, and there we go, perfect. We have this two, well, let's call them, it looks like a cell that's mid-mitosis, meaning it's dividing. Reason for this being 2 loops is 6 divided by 3 is 2. So if I were to upgrade this to 9 and execute the node tree, we get 3 loops and so on. I'm going to turn on auto execution, so this executes every time I change one of the values. And if they're not divisible by each other, there's going to be a lot more different loops. Okay, so if I increase the d, we increase the, well, let's call it variety, or the thickness of the rim, whatever you want to call it. I'm going to leave it at that. That's actually a interesting enough figure. All right, leave it at this. Good. So next thing I want to do is give this a third dimension. So of course right now z is 0, and if I put in 5, execute the node tree, everything will jump up by 5 Blender units, which isn't too exciting. So let's give z a function, just as this is a function. I'm going to give z a function as well. So I'm just going to go with the most simple function that I can think of right now. So I'm going to call it sine of t. I'm basically orienting myself on this one. And as I said, I did a lot of experimenting and just typing in random stuff, so it's sort of similar to this. And in the end, I had a result that I was sort of happy with. So this is fairly boring. So because it's a sine wave with exactly one peak, so that's pretty boring, valley and peak. And if I were to multiply this by 5, in theory, we should get 5 peaks. And we do. It's a bit hard to tell because of the structure of the figure. So I'm going to multiply this by 5. So I have more height difference, and there we go. You can see now we get a frequency. This looks pretty interesting already, but I want more control. Right now, if I wanted to change the amplitude, and maybe I want the amplitude to be attached to a sound or whatever, or just animate it over time, I need to go back into my script and change this 5, which of course is not something we want. So I'm going to do this and call it amplitude, amp for short, and I'm also going to turn off auto execution just in case. Go back down here, and now if I were to expose this value, which would be here, it's a float, and I'll call it amp. Important, same spelling. And this one I can call amplitude, whatever I want, and connect it here. Execute the node tree, it's flat again, and auto execution on. If I change the amplitude, you can see it grow. Not much of a surprise there. And let's make this a little more interesting. We have another 5 here, and the 5 actually determines the frequency. And if you're at all familiar with sine and cosine functions, you can have an amplitude, a frequency, and what's called a phase. The phase offsets the curve, which means if you were to look at it from above at the 2D projection of the sine wave, you would basically move the entire curve along the x-axis. We're in 3D right now, so the phase basically rotates our z values. Right now, of course, we get another error. Frequency and phase are not defined. So let's just change that real quick. float again. And this would be and this phase. And of course, 2 new here as well. And frequency, phase. And of course, connect the two. And I'm going to turn on the auto execution. And of course, it shrunk down to 0 because we're multiplying by 0. If I increase the amplitude, it still nothing happens, and that is because we're at sine 0 plus 0. So if I increase the phase, this actually, you can see it go up and down depending on where we are, but we want the frequency. That's a very important one. Okay, so let's say 3 or something. Here we go. And the phase, if we look at this from the top, no, that doesn't work. If we look at this from the side, the phase will do this. Make it wiggle or whatever you want to call that. Okay. So that's a lot more interesting, and we have a lot more control over what we're doing. And we could actually already leave it at that, but this is a tiny bit boring still. And since I spent hours trying to find out a formula, let me just share it with you. If I put a hashtag, I don't know what it's called in English, pound sign, yes. If I put a pound sign in front of this, you can see it's grayed out, and that means Python means pound, ignore this please. Now, if we were to execute this, we would of course get an error message because nobody knows what Z is. So I'm going to use a copy paste at this point because I want to type this. So basically, there you go. That would still work, by the way, but it's redundant. So, okay. So here I did something that's just very similar to this line, except for it has the frequency and the phase and the cosine frequency and phase. So basically we have some minus here, we have some plus here, so that's all I did with this one. Let's retry this and execute it again. That works. Okay, and phase makes it kind of bounce up and down. Frequency does something similar, and amplitude, of course. Amplitude is always a constant value, and right now it doesn't appear here. Well, it does appear here because my undo also undid the pound, but this completely overwrites whatever was in this line. Okay, so that was the first thing I did. It's a little better, but still pretty boring. So I added another line, which is this one, and you can see there's a minus in front of the equal sign. So now we're not assigning Z, we're subtracting this from Z. So let's execute that again, and you can see this is starting to look a lot more interesting, at least in my eyes. The phase can be 0 because we're just adding the phase. We're never multiplying by the phase, so it can be 0. Frequency should not be 0. And the phase kind of makes it wiggle. That's actually an interesting effect right there, if you ask me. And this looks pretty cool already, but I did one more thing with the Z. I multiplied it, and this works as well, by the amplitude, of course. The reason why I split this into 3 lines is I could very well just delete the Z, delete the equal sign, and put this behind it. First of all, my line would get very long, and second, if I want to multiply the entire thing by the amplitude at the end, I would need to put all of this into another set of parentheses, and I don't want that. So just for readability, I split this into 3 lines. It is not necessary at all, but I just preferred it. So let's execute one more time, and now we can use the amplitude in order to control the offset and the frequency. So now I think we're done with this. we have our 3D offset. If you come up with something that's even more interesting than this, and I have no doubt that some of you will, you can either leave the formula for Z in the comment section or contact us directly. If you want to use this construct in future projects, of course, feel free to do so. That's it from my side. My name has been Frederik Steinmetz, and please do try this at home.